Hello everyone, and welcome to Introduction to R, Part 5, Vectors. In the last lesson, we learned about variables, which are essentially named containers that you can store different values in. In this lesson, we're going to learn about our first compound data type, which is the vector. Now in R, a vector is essentially just a list of values that have the same basic or atomic data type stored in them. And to create a vector, you use the C function. So if we look at this code cell here, we are assigning a new variable the value of C123. And what the C does, it takes a comma-separated list of values you want to combine into a vector, and it just combines them and creates the vector for you. So in this case, we're creating a vector of these three values and storing it into the value x. And below here, we're making a different vector. We're using the C function and creating a character vector in this case with the values r, is, and fun. So when we run that, we can see that it produces a sequential list of the values when it prints out to the console. Now you can also combine two existing vectors with the C function. So you can see below, we can assign a new variable z, the combination of the first vector we assigned above, x, and the second vector, y. We'll run that and then see what the result of that is. As you can see, this vector looks a little weird because the 1, 2, and 3 are quoted, which means they were stored as characters, whereas above, this was a numeric vector. You can see these values are not quoted. So this is kind of a quirk of the vector assignment operator. If you try to pass in vectors or values to combine that aren't the same basic data type, in this case, we passed in both numeric values and character values, R will try to coerce or change the data types into something that makes sense or what it thinks you might have wanted. So in this case, it switched all of those numerics into characters so that it was able to make a new vector from this combination instead of having to throw some kind of error. Now, in some cases, you might not actually want it to do that, so you have to be careful about what sorts of data types you're passing into the vector constructor. But we can see the result is a 6-element vector of characters. Now, after you've created a vector, every single element of it is assigned an index, and that indicates the order of the values that are in the vector, and then you can use the index positions in order to look up values that are inside of the vector. So in this code cell, we're going to create some random data with the runif function. You don't have to really know what this means yet, but basically we're creating a vector of 100 random numbers, and then we will print the data to the screen. So we run that, and you can see we've printed 100 values, and when you print a long vector like this to the console in R, every line is given a number that indicates the index that that line starts with. So you can see here we have the number 1. That means this value here is at the first index position. This value here is at the 7th index position, etc. So this printing scheme kind of gives you some idea of where the different values are in the vector, which can be kind of useful because we can see here in this last line, the index 97 is this one, and there's only 3 more after that. So just from that, we know that there are 100 values in this data, even though we know that from when we made it. But if we didn't construct it ourselves and got this data from somewhere else, that would immediately give us a rough idea of how much data we had in our hands. And you can use the indices to grab values. So to do that, you use the square brackets after the vector, and then you pass in the index that you want to get the value at. So in this case, we're saying we want to take that random data vector we assigned earlier, and we want to get the value at the index 7. Now up above, we saw that the value is this 0.481. So when we run this, we should see that same value. There we go. Now, if you try to access an index at a position that doesn't exist, you will get an NA value, which is essentially a missing value. So here we're going to try to get the data at index position 200, but we know that that doesn't exist because this random data vector only has 100 values. So when we run that, we get an NA back. Now you can select more than one value at the same time using indexing, and this essentially creates a subset of the vector. And to do that, you can pass the range of values you want with a colon in between them. So here we're creating a new variable called subset1. We're assigning it the value of the random data vector, and we're getting only the values from index 7. We put a colon to say we want everything between 7 and 14. So this will grab all those values, and then we'll print them to the screen. So there they are. You can see this has created a new vector that then gets its own index. So this value that originally started at index 7 in the subset is now assigned index 1 because it's the first value in that new subset. You can also subset vectors by another vector, which essentially lets you grab specific values at specific index positions. So in the second subset construction, we're taking a new subset. We are taking the random data from earlier, and we are getting the values at index positions 1, 10, and 100. That's what happens when we pass in a vector of different values into the index construction. So this will grab those 3 values and print them to the screen. Another function that you can run on vectors is the length function. That will simply tell you how long the vector is. Now, you can use length on singular values as well, which will just show you that it's a vector of length 1. So if we run length on just the value 10, we'll get a 1 back. And if we run length on our random data variable, we should get 100 back because that's how long it is. So there we go. Another way to index into vectors is using a minus sign. And when you use the minus, it excludes the index you pass in instead of grabbing that index. So in this case, we're making a new vector called y, called r is fun, with the value r is fun. And we're saying we want to index into it, and we want to get everything that isn't at the index 2. So in this case, instead of grabbing the index 2, which is the value at index 2, which is, we're saying we don't want that, and we want everything else. So in this case, it'll cut out the is and leave us with r and fun. There we go. The minus sign is also capable of excluding ranges of indices. So we saw earlier that we could get a range of values by passing in a value, a colon, and then the ending value for the range. Now, if we use the minus sign, it will exclude all the indices instead of getting all those. So here we're assigning random data, some new random values, only 50 this time. And then we are getting a subset where we're excluding every index except for the first one and the last one, 1 and 50, because everything in this range is excluded by the minus. So the result should actually be a vector that only has 2 values left in it. As you can see, this was the first value and this was the 50th value. Everything else has been cut out by this index construction here. Now, a final way of indexing into vectors is using logicals. So if you pass in a logical statement to the indexer of a vector, it will grab every value where that logical operation is true and exclude every value where it is false. This is one of the most common and useful ways of indexing into data, especially when you have large data sets where you aren't generally going to be indexing into specific values, but you might say want to get every value that's greater than the average or something like that. And that's what logical indexing allows you to do. So here first we're creating a logical index where the random data is bigger than 1/2. We're going to print that to the screen. And then we're creating a new subset of all the values that were bigger than 1/2. So we're taking the random data. We are using this logical index, which is just a sequence of true-false values. And we're using that to index into the random data to only keep those where this random data greater than 0.5 is true. So since this was created with a uniform random function, there should be around 25 values in here, but since it's random, there could be a few more, a few less. So let's run this. You can see first, this was the logical index. So for instance, at index position 1, the value was true, which means index position 1 had a value bigger than 1/2. Position 2 was false, so that value is dropped. And then we passed that into the indexer, and we got the values back. And we can see there are around 25 values. 2, 3, 4, 5. So maybe there were around 26, so that is pretty close. And you can also use what's known as the in operator to do indexing or to do logical comparisons. And the in operator basically checks whether some given value or sequence of values exists in some other sequence. So here we're assigning my letters a vector A, B, C, D, A, A, F. And we're saying we want only the values that are contained within this vector AC. So basically we're saying we want the values in this variable, my letters, but only the ones that are in this second vector A and C. So basically anything that's not an A or a C is going to be dropped by this. And we can see that 1, 2, 3, there's 4 things that shouldn't be dropped. So let's run this and see what happens. Here we go. We've gotten all the A's and C's, and everything else has been dropped. Now, one of the really nice features of vectors in R is that the whole language is built so that vectors do what's known as vectorized operations. So when you try to do most types of mathematic operations and even run functions on vectors, they often operate in an element-wise fashion where each element of one vector is combined with the same element at the same index position in the second vector. So as an example, we'll make this vector 1, 2, 3, and when we add the value 10 to it, it simply adds 10 to every single value in the vector. And in the same way, if we subtract, it will subtract 10 from every single value in the vector. That just happens automatically in R. With vectors, you don't have to specify any kind of loop to do that sort of thing, which is quite nice. So if we run those are the results. And other math operators work as well. So the multiplication, division, exponentiation, modulus, everything we've learned about in the previous lessons for mathematical operations all work like that on vectors. So if we have this vector here, for instance, and we run round on it, all the values in it will be rounded. Same thing with floor. All the values in this vector will have the floor operation performed on it. They have all been rounded, and these have all been rounded to the floor. And as I said earlier, vectorized operations make it easy to perform things in an element-wise fashion. So if we have, say, 2 different vectors with collections of values, here we have a vector 1, 2, 3, 4, and here we have one 10, 20, 30, 40. To add those together, if we add those, the addition will be performed in element-wise. So 1 will be added to 10, 2 will be added to 20, 3 will be added to 30, and 4 will be added to 40. Same thing with multiplication. So the 1 will be 1 times 10, 2 times 20, 3 times 30, 4 times 40. If we run those, we will see the results. So whenever you're performing these vectorized operations, you're getting back a vector of the same length as the original one. If you want to perform actual dot products, which is multiplying all the values element-wise and then summing them up, instead of the normal multiplication operator here, you use the multiplication operator, but you put it inside of these double percentage signs. So in this case, we're actually doing the full inner product or dot product on these two vectors, and that will return a single value then instead of the sequence of 4 here. We'll run that. The result of that is 300. Element-wise operations can also work on character vectors if you're using functions that allow you to pass in characters. So for instance, the paste function takes two characters and combines them into one, essentially pastes them together. But if we pass in vectors of characters, it will paste each together in an element-wise fashion. So when we paste together these two vectors, we're going to end up with another vector of 3, but it's going to be a combination of both of them. So the first character instead of R is going to be R Kaggle, then is, and fun. Let's run that. And the type conversion functions that we discussed earlier for atomic data types also work on vectors. So if you have a vector of numeric or doubles here, we'll check the type, and then you use as.character to turn it into a character. That will work on and change every value in the whole vector to character. Let's check that. Starts off as doubles, and we've converted them all to characters. Now, generally, you won't want to be creating huge vectors of values by hand. Oftentimes, you'll be loading data into R from an external source and get data that way, but there are also many ways to generate vectors of longer lengths without having to explicitly write them out by hand. So it's good to know how to do some of those. If you just want to make a vector of sequential values, you can use the colon operator. So here we're assigning x a vector of the values 1 to 20. That essentially creates a range that is populated with every whole number between the range. If we run that, x should contain 20 values, 1 to 20. There we go. There's also alternatively a function called seek for sequence, and that will allow you to create a little bit more complicated sequences that maybe skip numbers. So to use the seek function, you type seq. The first value is from. That's the value the sequence starts at. And then the second value is the argument to. That's where you want the sequence to end. And then the third argument is by, which is how many values you want to skip in between each value of the sequence. So if we wanted to create this sequence of 1 to 20 like we did before, we could do the exact same thing by using sequence from 1 to 20 by 1. Maybe I'll just change that real quick and show you. So that's the exact same sequence as above, but we could, for instance, put 2 here, and then we're only counting every other number. So if we run that, it creates a sequence that's only 10 in length, and it's all the odd numbers instead of all 20 of them. And you can count by really any value you want to, so we could have counted by even a decimal, and that gives us 40 values. So that's a pretty useful way of making sequences of different sizes. There is another function called rep, which allows you to simply repeat a number or a vector a certain number of times. So with this construction, we are using rep to repeat the number 1 10 times, and that will give us a vector of 10 ones. So that can be a useful way of just populating large vectors of different types, or perhaps repeating a vector several times. And as we saw earlier, you can generate random numbers using the runif function. So what that does is you pass in the number that you want to generate. So in this case, we're generating 5 numbers. And then you specify the range of values you want to generate from with the min and max arguments. So here we're generating 5 random numbers between a minimum value of 0 and a maximum value of 100. Run that. So that concludes our first look at vectors. Now, real world data is often stored in two-dimensional tables with records that each have variable values. So it's essentially a table of rows and columns. And a vector only has one dimension, length. So in the next lesson, we'll learn about our first two-dimensional data type, the matrix. So look forward to part 6, matrices.